45.0241. We have 7 minus 14.71. Square that gives us a value of 59.4441. And we have 22 minus 14.71 gives us a value of the square that gives us a value of 53.1441. We have 18 minus 14.71. Square that gives us a value of 10.8241. And we have 16 minus 14.71. When we square that, that gives us a value of 1.6641. And finally, we have 20 minus 14.71. When we square it, it gives us a value of 27.9841. And actually, let's sum up them values here because we need a sum of squares. So we have 7.3441 plus 45.0241 plus 59.4441 plus 53.1441. I don't know why I'm carrying all these decimals around me. I should have rounded. Plus 10. Delete that. Second function, delete that. Okay. So what did I say? 10.8241 plus 1.6641 plus 27.9841 gives us a value of an error, would you believe it? Let's do it again. 7.3441 plus 45.0241 plus 59.4441 plus 53.1441 plus 10.8241 plus 1.6641 6651. So if I take away, I'll do that in a minute, plus 27.9841. I'm just gonna, because I increased that by, so it should have been 1.6641. So if I take away 0.001, okay, which gives us 205.4287. okay, so our S is going to be the square root of the sum of the x's minus the x bar squared divided by n minus 1, which gives us 205.4287 divided by n is number of paired observations, in this case the 7 minus 1. So we have, it's the square root of that. So when we take that, we have 205. We have, let me just do that down here, 205. Let's do the square root. Square root of 205.4287 divided by 6. Okay, 7 minus 1, 6. That gives us a value of, well, there we go, 5.85 approximately. Okay, so now we have S. So we effectively have everything that we need. Okay, I'll just put this down here. So S is equal to 5.85. So now we're in a position to calculate this point-biserial correlation, which is the correlation between which is the correlation between a dichotomous variable and an interval variable. So now we have the correlation, or PB for point-biserial, is the average of the first proportion, which is 9, minus the average of the second one, which is 19, divided by the standard deviation of the interval variable, which is 5.85, and multiplied by, okay, the square root of the first proportion, which is 0.43, times the second proportion, which is 0.57. okay, so when we work this out here, we get, well, what we have here, we have minus 10. So we have minus 10, so negative 10 divided by 5.85. That gives us a value of that, and multiply that by the square root of 0.43 multiplied by 0.57, which gives us a value of, there you go, or PB is minus 0.85, and that's our correlation coefficient. And we interpret this the same way as we interpret any other correlation coefficient, on the scale of minus 1 all the way up to plus 1. We have 0, we have, let's say, 0.5, 0.3, we have 0.1, minus 0.1, minus 0.3, minus 0.5, and we have all of these intervals. It's either perfect if it's equal to plus 1 or minus 1. If it's less than that and greater than that, in other words, if it's greater than that and less than that, it's strong. strong positive, strong negative. If it's less than that and greater than that, it's moderate or medium. If it's less than this but greater than 0.1, I suppose, let's say it's weak. It's weak, and it's between them. If it's between them, there's none. Okay, and the same over this side. So you can actually see in our situation we get minus 0.885, which is actually in here. So what we're saying is that there's a strong negative association between gender and spending behavior. Okay, there's a strong association between spending behavior across the genders effectively. Okay guys, once again this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and I hope that this video was in some way intuitive, and more importantly I hope that was helpful for you, and thanks for watching. Okay, bye bye.